Okay, here's another exam problems dealing with thermodynamic cycles. Um, okay, so on the left we have a thermodynamic cycle. Okay, and we have our standard like PV diagram here. So pressure, vol volume here. And we want to find the total work W done in a complete cycle, expressed in terms of B, C, D, E, the pressure for these points, and then the volume at A and B. And then we want the efficiency of the cycle expressed in terms of the temperature at D and E. Okay, so we're going to hope to figure out how to cancel some stuff there. So the gas used has a given value of gamma. So we have this gamma. We're going to assume that it's known, and then we're assuming that all of our um, pressure values are also known. So okay, let's try to set some stuff up here. Okay, so let's go ahead and get into this. So we're told that we need things expressed in terms of pressure at B, C, D, and E. So PB, PC, PD, PE, and then the volume at A and B. Okay, so that's what we're allowed to use. So before we get started, let's look at how we could maybe um, relate a couple of other things. So if we know that, I'll just lay these out first so that we can sub them in later when they turn up in other expressions. So we can kind of be aware of what won't be a problem for us. Okay, so I know that this is VA here, but because this volume is on the y-axis, everything on this y-axis is the same value, right? So I also know that VC is equal to VA and VD is also equal to VA up here. All these points are equal. Okay, so what about over here? This is VB. We also know that VE is equal to VB because they both share the same point. Okay, so just kind of keep that in mind before we get started. So we're allowed to use those. We're also told that the gas use has a known value for this gamma. Okay, so we know this. So we're trying to find our solution in terms of these variables. So step one, we're going to look for the total work. Okay, so what I did was I went ahead and I made a table for the total work, and I want to kind of walk you through what is going on here and why I have these things. Okay, so I'm going to look at the lecture notes and kind of go through things one by one. So we're told that from A to B, right, or I'll just stay over here. We're told that from A to B we have an isobaric process. Okay, so I want to look for work because I'm looking for total work, and my equation for net work is going to be all of these things added together. So it's going to be the AB, BC. I'll erase this because I'm maybe one step ahead here. It's going to be all of these added together, right? So the work contributed by every single process in the cycle. Okay, so um, let's see what each of those individual processes would contribute. So we're going to look at isobaric. So going to page 28, we're looking at page 28. Um, First, we have isobaric. So for isobaric, we're going to look at the work for the isobaric term. We have W is equal to the pressure times the change in volume. So uh, volume is moving across this direction, and notice that the pressure is static. So if we look at this graph, we can kind of see isobaric means that we don't really have a change in pressure. Okay. All right, so let's go next to isometric because that'll be a little bit easier. So isometric and isovolumetric, those two are the same. So we have 0 for our work. So uh, our work is going to be based on a change in volume here. And notice that the pressure changes with the volume's constant, so our work here is going to be 0. Okay, so that's what we know. So we plugged in this general equation for both of the isobaric terms and then for the isometric terms. Okay, um, now I want to note something really interesting, right, for isobaric. So we have pressure times the change in volume, and we're integrating, right, when we look at that. So when we have the change in volume for isobaric, if we go back up, uh, for that isobaric system, it's the pressure times V2 minus V1, right? That's what gives us our positive change when we're going from A to B. But then when we're going backwards, we're actually going to end up with a negative version. So we know that the work from A to B is going to be equal to, or is work from A to B is going to be, or the work from B to A is going to equal negative work from A to B. Okay, so when we do our net work, we're going to notice these two terms are going to end up canceling each other out, right? So just keep that in mind. Okay, before we do that, I want to set up the general equation for work for the adiabatic process because that one's going to be the more complicated version. Okay, so let's go down to adiabatic. So I just based on what this equation is asking us for, we can put work in this term, but that's actually going to make things more difficult for us. So instead, I am going to kind of follow the solution guide's lead here. And when we have an adiabatic process, sorry if I'm zooming too much, we know that our change in energy is equal to negative work. So we're going to say work is equal to the negative change in energy. Okay, so we're going to go up and we're going to take our equation for change in energy, which is this d over 2 is equal to P2V2 minus P1V1, and we're going to put that in there. Okay, so we're going to have negative d over 2, right, times P2V2 minus P1V1. So we don't have this value for d over 2 in the problem, but we are given this gamma. D represents the degrees of freedom for a gas constant, and we can also write d over 2 is equal to 1 over 1 minus this gamma term, because gamma is equal to 1 plus 2 over d. So you can work out the algebra for that and prove to yourself if that is true, but for right now you can also just take my word for it. Okay, so then if I put that in terms of the variables that we do have, so I have 1 over 1 minus this gamma to sub in for d over 2. And I'm going to take the negative and I'm going to use it to flop the terms. P1V1 minus P2V2. So same general expression for work for an adiabatic term for both of them. So I'm going to go ahead and take this out of the way because I got what I needed from it. Okay, so now what is P1 V1 and what's P2V2? So I'm going to actually erase this because I said this before. I'll just make it smaller and kind of move it up here because we're not going to use this definition anymore here. So we really need it, and I want to try not to keep things too cluttered. Okay, so if we're going from A, oops, not from A to B, what are we going from? We're going from B to C. So we're going from B to C. So this would be our 1 and this would be our 2, right? So if I want to simplify my expression, 1 over 1 minus gamma, what is 1? I have P B VB, right, minus PCVC. Okay, because B is 1 and C is 2. So going from B to C. Okay, so let's do the same thing over here for this guy. So same general equation, same everything. And let's plug in what we would have. So that would be times P1 V1 minus P2 V2. So just kind of skipping some steps there, which is fine. So 1 over 1 minus this gamma times P, and where am I starting from? I'm starting from D, so it'd be P, D, V, D, and then I'm going to E minus P, E, V, E. Okay, so let's put together my general expression for work. So I solve for each of these work terms separately, just kind of using the lecture notes for the general equations. Okay, and I found all of them. So now I'm going to say, add them together. I'm going to take this WBA term, I'm going to turn it into a negative WAB, okay? And I can cancel these guys, right? These will cancel. I know that CD is 0. I know that EB is 0. And then my final terms I have are just these. Okay, so what is my net work? W net. So what's left? So I have BC. Okay, so I'm going to take what I got for BC, copy and paste. Okay, WBC, and then I have WDE, right? So I just have the work from the two adiabatic processes. Okay, add those together. So now I'm going to group like terms, and then I'm going to look and see if my answer is in the form that the problem asks for. And if it's not, ask myself what I need to do to get it that way. So I have W net 1 over 1 minus this gamma. And I'm going to, because it's multiplied by both terms, I'm just going to kind of pull it to the outside and then group like terms on the inside. Okay, so I have P B V B minus P C V C plus PdVd minus PeVe. Okay, so what did the problem tell me that I was allowed to use? What solution form did I have to get this in? Well, I have to have it in terms of these guys here, right? So I can have any subscript for my pressure, but I need everything in terms of VA and VB. Okay, so that's going to be a pain for me. So I know that VA is equal to VC, VD, and I know that VB is going to be equal to VE. So I'm going to copy these and take them down. Okay, so in my expression, I have some things that I'm not allowed. So I can have, remember, pressure with all of these subscripts, that's fine, but I need to have everything in terms of VA and VB. So I'm going to swap out, so VC is equal to VA, and then VD is going to be equal to VA, and VE is going to be equal to VB. So I'm going to have to swap those. Okay, so my network, W net, is equal to 1 over 1 minus gamma times PBVB minus PCVA plus PDVA minus PEVB. Okay, so let me just double check the solution guide that they have here and make sure that I don't have an error here. So PBVB, PCVA, PDVA, PEVB. Yep, and that is correct. Okay, so just to recap what we did. So we looked at the problem. We looked at the solution form that we needed to get things in. Before we started, we looked at the equivalent volumes just by looking at the graph, so if they shared the same y-axis. Then we did a table, okay, and we figured out work for each of the separate processes. And we did that by looking at the lecture notes, okay, and finding the general equations for work, okay, paying attention to the sign conventions, okay, and then we were able to combine all of our terms here, and we got to the bottom here and we basically just swapped out the volumes that we had left. So yeah, so essentially we took the labels for the processes and we just sort of looked up the equations that we needed, got them in the form that we needed, so manipulated them a little bit using what we know about this gamma term and the degrees of freedom for a gas. Okay, so I'm going to go ahead and stop this and then move on to the second part where we find efficiency.